Alright, so I will do a few area problems today. And those will be about area between curves on a plane. So that's the common topic for the whole class. And so the first problem, find the area of the region bounded by y equals x squared over 5, y equals minus x, and the line x equals 4. So the first thing about this problem is to recognize what kind of region the problem is talking about. And for that you need to sketch the graphs of all these functions. And the functions in this example are simple, so we can easily sketch them. So the first one is parabola, the second is a line, so this is y equals x squared over 5, that is y equals minus x, and there is a vertical line x equals 4. Now, what is it exactly that the problem is asking for?
The area of that.
The area of that region, right? Notice that these curves, these three curves, cut the plane into many different regions. And of course, some of them are not bounded. And for those, immediately you can say that the area is infinite. So those are of no interest to us. But there are two bounded regions that we can see. And then, by reading the statement carefully, you can recognize that there is only one of those two that is bounded by those three curves, right? Because this one is bounded by two of them only. So the question is only about the area of this region, kind of triangular region. Now, once I recognize that, I would like to check that integration is useful. So I will check those two quick things: additivity and differentiability. So what about additivity? If I cut this area into pieces, the area of the whole region is equal to the sum of areas of the pieces. So in this case I can say that area is additive. And that property is not a part of calculus, that's the part of geometry. Then differentiability. So what is it that I'm talking about here? I'm talking about the area as a function of, I need parameter, right? For integration I always need parameter. So I will take x as my parameter. And it changes between 0 and 4. And then the idea is to use rectangles. So the basic shapes I'm going to use are rectangles, and for those, area of a rectangle is equal to width times height. And the idea now is that if I cut my region by vertical lines, then those vertical pieces will look like rectangles. And the area of such a piece is going to be approximately. So what I hope for from the point of view of integration is to have it approximately being a product. Something times delta x. So delta x times something, right? And then geometrically delta x is going to be the width of the shape, and then the height of the shape will be something independent of delta x. Height is going to be something independent of delta x, and the shape will be approximately rectangle with that width, that height. And that's exactly what it means for area to be differentiable with respect to x. You can represent the little change of the area in terms of little change of the argument linearly. Alright, so this is just a quick check of the fact that integration will be useful. And now we will go ahead and proceed with the setup. So I will again say what my model case is, linear case, when I can actually compute the area exactly. This is about the area of rectangle, which is width times height. And then I choose my parameter for integration. And the parameter is going to be x, and it will change from 0 to 4. And then I will subdivide this interval into short subintervals. Of length delta x. And then this subdivision of my interval will make subdivision of the area into pieces. So then the region is subdivided into subregions. And what's important about those regions, about those little regions? They are approximately rectangles, which are approximately rectangles. And this is exactly what allows us to say that then the area, if AI is the area of ith region, then AI is approximately the height times the width. So width is going to be delta x, height is something that depends on the region, depends on I. And of course the total area is exactly equal to the sum over all I of my pieces, and this is exactly the additivity. And then I use my approximation, saying that each area is approximately height of ith region times delta x. And then I claim that the area is going to be the limit as delta x tends to 0 of those sums. And what I need now is to figure out what this height is so that it depends on x. So what is the height? Well, the height is going to be geometrically this vertical distance between the two graphs. So what we can say is that if we call this graph f of x and I call that graph g of x, then the height is going to be the difference between the value of f and the value of g at some point. It's f of xi minus g of xi. And since I know the formulas for f and g, that is going to be just a function of xi. And then, once I see that this is a function of xi only and not of delta x, and I have a product with delta x, sum and limit, so that's the integral by definition. Integration happens from x equals 0 to x equals 4. The function I need to integrate is going to be f of x minus g of x, and I integrate with respect to x. And the rest is, of course, a simple computation. You have to integrate from 0 to 4. F of x is x squared over 5. G of x is negative x. And I will not finish because you can stick this into Wolfram alpha, it will give you the result. The most important part is the explanation of why that integral is useful and will give you the area. Now, let me illustrate this step right here. When I said that those approximations become the area as I take the limit. So I borrowed this demonstration from Wolfram demonstration project. If you go to Wolfram website, there are thousands of demonstrations like this on different subjects, including calculus. And this is the one about area. Sorry, I lost my mouse. Here it is. Right. So basically it allows you to visualize the functions, and my problem was exactly about these two functions. And they take it exactly on that interval from 0 to 4. Now what happens is that I can interact a little with the program. I can choose different functions if I want, but for this example, what I need is to play with this number of segments. Right, so this is exactly what happens here when I take limit. I look at the subdivisions of given length delta x, and then I compute the approximation, and for this given one, the approximation is 10.6, and the area is given. You can see how close that is to the actual answer. And then I can approximate better, hopefully, and you can see that indeed this approximation is better. So it's approximating from below and it's increasing. And the fact that it's approximating from below is visible geometrically. All these rectangles are completely inside the region. And you see that to get to the number 12, you need many pieces, right? You need delta x to be very small. And having 30 little rectangles doesn't even get you close to 12. And then you have a choice of right side approximations and left side approximations. You can also play with that. The right side approximation makes all these rectangles bigger than what I need. And since all of them are bigger and the actual region is within the union of all of those rectangles, my approximation 15.2 is greater than the actual value. And then again, I can play with those approximations, and it's hard to get below 12.5. And actually I don't, even subdividing into 30 pieces. And you can also play with this center. Well, remember, the center means that for each rectangle, you compute the height by choosing the center of that region and computing the difference of values above the center. And for the center, you see how close I am already with only 5. Right? And that's because choosing the center, you underestimate on one side and overestimate on the other, and those cancel. Not exactly, but with very high precision. So I'm not saying that choosing the center is always great and much better than left hand or right hand. And ultimately we are always looking at the limit. But you can see that this idea of taking limit, it sometimes depends on technicality, on how you choose those points, how you approximate by rectangles. And then for some choices you may see quick conversions, for some choices you may not see conversions for quite some time. So it's only our belief at this point that what we see, the approximations, converge to some number as the delta x goes to 0. So that's exactly what we claim here, that we believe that what we wanted is the limit. All right. Any questions about this problem?